The broadcast is now starting. All attendees are in listen-only mode.
Hello, everyone. Thanks for joining us today. On behalf of the Environmental Finance Center Network, I would like to welcome you to our webinar today on reducing water systems costs through energy efficiency. My name is Savannah Bekowski, and I work at the Syracuse University Environmental Finance Center. We have a great webinar lined up for you, but before we jump into the presentation, there are a few logistics that we do need to cover. First, everyone will be kept on mute to ensure audio quality of this webinar. If you have a question, please type it into the question dialog box on your GoToWebinar control panel. Feel free to submit questions and comments at any time throughout the session. All questions will be reserved for a Q&A at the end of the webinar. We will be posting both the presentation and video recording of this webinar on our website, and you can reach it at that URL in the bottom left, www.efcnetwork.org. You will also receive a follow-up email that includes a link to all of this information. We do not submit our webinars to licensing agencies for pre-approval of continuing education credits. We will provide certificates of attendance as a courtesy. If you have joined this webinar with the intention of using it to support CEU hours, please know that it can take 1 to 2 weeks to generate the attendance certificate, because we must verify your attendance for this webinar. You must have joined this webinar using the unique join link you received when you registered. Again, we cannot guarantee that this webinar will meet all requirements for specific CEU or licensing renewal needs, but if you do have any questions about this, please email us at smallsystems@syr.edu. And for just a little bit about us here in the Environmental Finance Center Network, our program provides training and technical assistance to small public water systems in all U.S. states and territories to help those local water systems achieve and maintain their goals and stay in compliance with the Safe Drinking Water Act. And here you can see the various centers that make up the Environmental Finance Center Network. There are centers and partner organizations spread throughout the country, and we all work together to create solutions for difficult how-to-pay issues of environmental improvement and protection. And so on that note, I would like to welcome our speaker that we have for today's webinar. We have Neil Worthen, the Environmental Training Specialist with RCAC and the Environmental Finance Center at Region 10. Neil, welcome. I'm going to pass everything over to you.
All right, thank you, Savannah. Let me get my screen loaded up here, and it sounds like we're ready to go. Thanks again for that great intro. Today we're going to be talking about how to reduce water system costs through energy efficiency, that water-energy nexus. There's a direct correlation between the cost of the water that our consumers are paying for and what we are paying for energy. Using energy to produce and treat and distribute water and wastewater and collect wastewater is quite inefficient. And we'll talk about why that's inefficient and basically how to save you some money on energy costs. That's what this workshop is all about. That's my smiling face. I'm speaking to you from Las Cruces, New Mexico, which is kind of the western edge of our working territory. Let me get my pointer working here. We are part of a nationwide organization called RCAP, the Rural Community Assistance Partnership, kind of divided up the country into 6 regions. RCAC, for whom I work, is the Western RCAP, and we cover the 11 Western states all the way out to Alaska and Hawaii, and we provide our range of services. Most of our funding comes from state and federal grants. We also have some private foundations and individual investors that help us provide assistance and training to rural communities throughout the country. And as Savannah said, if you have any questions or comments, go ahead and type them in. Savannah will be watching for those, and we'll have a time for Q&A toward the end of the session. Today's learning objectives. To be able to actually perform a cursory energy audit of your facility, no matter how large or small, and try to achieve a quantifiable reduction in monthly energy cost. This is all about saving you money and reducing costs. Also, for you to be able to identify and select energy efficient lighting and equipment, and be able to calculate, and this is kind of the bottom line, the simple payback in years of retrofitting new equipment or replacing old obsolete equipment with more energy efficient equipment. So let's talk about some just general facts about electricity or energy in the United States. A large percent of a surprisingly large percentage of the electricity used in this country is for water and wastewater facilities. Again, producing and distributing and treating water and also treating wastewater. U.S. energy costs are predicted, these figures come from U.S. Department of Energy, are likely to increase 20% by 2035. That's just 15 years away. And despite all of the great discoveries of natural gas and the new technologies of fracking and so forth, and the tar sands that we're getting producing oil from Canada, energy costs are still predicted to increase. And again, the idea is to get you thinking about that and get you thinking about things that you can do to reduce those costs. Right now, about $4 billion are being paid for energy by water and wastewater systems, basically small and large communities all across the country. That translates to 56 billion kilowatt hours and 44.8 million tons of greenhouse gas. So if we could achieve a small percentage of reduction, that would be a good thing. Many of the small communities that we, being RCAC, and most of the environmental finance centers work with and assist, water and wastewater energy use can often consume 30 to 60% of a small rural community's budget. I know when I was a public works director in California for quite a few years, that was right in line with our budget. About almost 50% of our whole budget was for energy use to treat water and wastewater. So if we could just achieve a 10% reduction in that amount of outlay, it could save $400 million nationwide and actually stop the production of 5 billion kilowatt hours. Many of you remember well, some of you, I should say, might remember the Arab oil embargoes of the 1970s. I actually started in the water and wastewater business back in 1979. Jimmy Carter was in the White House then, and the idea of energy conservation back then was to sit in the dark with a sweater on. That was what we were dealing with. That's when you may remember the nationwide 55-mile-an-hour speed limit on the freeways, gas lines at gas stations all across the country. That's when the United States was largely dependent on Middle Eastern countries for about 60 to 70% of all of our energy in the form of oil. We have since completely turned that around in the last few years. But energy efficiency is not energy conservation. Efficiency is the process of doing more with less, basically to accomplish the same tasks or more tasks and functions as we did before while using less energy, but without compromising water quality, without compromising safety in the workplace and also the public health of our customers, without compromising regulatory compliance, and in the case of HVAC, without compromising our own comfort. So we're trying to take less energy and actually do more with it. So one of the goals of the workshop today is to give you the skills and information you need to actually do an energy audit, a cursory energy audit. So let's start by defining what exactly is an audit. I mean, we've all heard that term. If you look up that term in Webster's dictionary or any other dictionary, you're likely to come up with that definition that's on your screen. Basically, any kind of a methodical examination and review. But in terms of energy, when you set about to do an energy audit, you're going to be analyzing the energy usage in your facility. And the idea is to identify ECOs. Now, I'm not going to be bandying about a whole bunch of acronyms because they're just confusing, but An ECO, if you ever see that acronym, that means an energy conservation opportunity. And that's just a fancy word for a mechanism by which you can save money on energy. And that's what we're going to be looking for when we do this. Let's get back to a few basic terms. Back when we all suffered through physics in school, energy is the capacity to do work. And energy is measured in kilowatts, units of 1,000 watts. Power is the amount of work being done over a period of time. And in this case, we'll use the generally widely accepted term of kilowatt hours, which is thousands of watts of energy used per hour. So for electrical systems, that's the simple conversion for kilowatt hours. For thermal systems, when you are dealing with furnaces and air conditioners and water heaters and so forth, it's BTU per hour, which is British thermal units times hours. And there's another one of those arcane acronyms, British thermal units. That is the amount of energy needed to raise or lower 1 pound of water by 1 degree Fahrenheit. And just for purposes of trivia, that has often been compared to or quantified with the amount of energy. Remember those big, large wooden kitchen matches that we used to use? I think they're still available, but they're harder to find. If you strike one of those large wooden kitchen matches and let it burn down to the point where you can't hold it anymore, that is about a BTU of energy, of thermal energy. So just for reference. So let's use kind of an example that we're going to use in our energy auditing that you're going to use when you're auditing your facility. You've got a 27 watt CFL, that's compact fluorescent lamp, and it's running 10 hours a day, 5 days a week. So let's say that would be a typical lamp that you might have in an office situation, or maybe your lab or your break room or whatever. So the power, the demand on the grid, the instantaneous demand is 0.027 kilowatts, basically 27 watts divided by 1,000. Now, I'm going to be throwing a lot of figures at you in a very short time. I would recommend not trying to memorize all of the figures and equations. The better approach would be download the presentation, as Savannah described, download the whole presentation. All of these formulas and equations will be available to you so you can use them, at your leisure without taking notes. So the demand is 0.027 kilowatts. The energy use, the cumulative energy use over a period of time, if you run through all the numbers, factor in hours, factor in days, factor in number of weeks, we come up with a little bit more than 70 kilowatt hours per year. That is for that single 27 watt CFL that we have in our office or our homes. So those are a few basic terms. That's kind of going to be your compass that we use to do this. So who can do an energy audit anyway? Well, I can, and my organization can. There are also lots of nonprofit organizations that may be funded by state or federal grants that can come to your location and do an energy audit. I happen to have passed the exam for certified energy auditor. The national clearinghouse for certifying energy professionals is called the Association of Energy Engineers. They're kind of like the AWWA of energy. They are based in the state of Georgia, and they issue certifications for certified energy auditors, certified energy managers, and other certified positions within industry. Architects and engineers have been trained to do energy audits, especially civil engineers. Some engineering firms actually specialize in doing that. Your utility provider very often will come to your location as a customer service and provide a cursory energy audit of your facility. Any technically proficient persons, and that means you have the skills to perform a cursory energy audit of your facility. And again, my goal is to give you some of the tools you need to do that. It's actually easier than it looks. Why would we want to do this? Auditing your facility for energy use, or even your home, provides a lot of different benefits, especially for a large facility where you may be spending many thousands of dollars a year on energy. It allows you to do some benchmarking. It delivers some key performance indicators, and mainly by that we mean dollars spent on energy per million gallons treated or produced in terms of water or wastewater. We want to come up with a cost per gallon, energy cost per million gallons. It also helps you identify trends. Are your energy costs increasing over time, but your water production isn't? You know, that might give you the information that maybe you've got some pumps that are wearing out, or you've got some other things going on within your facility where energy use per gallon treated is slowly creeping up. It also gives you a decision tool for changes in terms of retrofitting obsolete equipment, maybe some budgeting tools. It helps you project your budgets in terms of capital improvements and what you might want to do in the future. We already talked about budget planning. It also helps you understand your system and how it works. It can help you track down things like water loss. Oftentimes a water audit and an energy audit can be done concurrently, and you can track down not only energy waste, but also water waste. So it really helps give you a much stronger knowledge of your actual system. It also can help you track down errors in your billing, errors in your payments that you made to your energy provider, maybe some meters that are falling behind and not registering properly, chemical usage, all of these things. An energy audit can help provide a lot of information, background information about your facility. So how are we going to start this? There are some steps that you want to take. The first is to understand your own billing. That starts with your energy tariff. The tariff that you have with your energy provider, that's your contract with them for them to reserve capacity for your use. Most energy providers, most electric utilities have many, many different tariffs. There is a tariff for security lighting. There's a tariff for street lighting. There's a tariff for high power use, a tariff for low power use, a tariff for high demand, a different tariff maybe for residential uses. They're all a little bit different. And the first step in an energy audit is to work with your energy utility and make sure that you're on the right tariff for your yearly energy usage. Sometimes just a phone call and talking with your utility's consumer advocate can help save you thousands of dollars by moving you from one schedule to another, one tariff to another. You also want to understand your quantities. We've talked about some of those quantities. kVAR is kilovolt amps reactive, and power factor. This webinar today doesn't get too deeply into those, but you can find out a lot more information on those. The second step, and probably the most important one, and maybe the most time consuming, is to understand your own facility. Now, most of you already do, especially if you are operators or facility managers. Understand your own processes, your own flows, what your requirements are, your peak daily demand, your peak hourly demand. Understand your equipment, especially how old it is and how well it's running and how well it's controlled. And then understand the goals that you want to set. You know, a typical goal would be you go to your board or your decision makers and say, we need to reduce energy costs by 10% within the next 12 months. That would be a concrete goal that's pretty achievable most of the time when we're doing these audits. So the physical audit starts with actually getting your hands on the equipment. Look at all of your equipment. You want to create an inventory of all your different equipment, which would be pumps, motors, lighting, air conditioners, heating units, actually what we call plug loads, which are all of the 120 volt items that we have plugged in at the office: battery chargers, computers, lamps, lighting, projectors, things that are not normally, things that are not normally connected with actual production or treatment of water, but are necessary to the operation of the business. Printers, things like that. We call those plug loads. Very often when we go through an office and we look and see all the appliances, computers and printers and chargers that are plugged in, and we go into the break room and we find, what do we always find? There's a coffee maker, or in some cases, several coffee makers that are plugged in, and that hot plate is running all day long, probably drawing about 600 or 700 watts for 8 hours. Those are the kind of things that really add up when you look at energy use over a whole year. Is the equipment outdated? Is it worn out? Is it being controlled properly? In other words, do you have occupancy sensors on your room lighting that turn the lights on when someone walks in and keep the lights on as long as someone's in there working, and when they walk out of the room, turn the lights off? Such things as pump controls. When a remote tank calls for water, are all those controls working properly? Then we want to evaluate what the engineer gave us in terms of design versus how it's actually being used. Can we adjust something to reduce energy use? Can we reduce something? Can we turn a pump off at certain times? If you're on time of use energy metering, can we have all of our large loads running when energy costs are inexpensive, and turn all those off during peak energy rates? Can you eliminate something? Eliminate a pump, eliminate a light. If you've got a whole treatment area with high bay lighting way up on the ceiling that has 4 fluorescent tubes, can you take 1 or 2 of those tubes out for each of the fixtures, and again, still not compromise employee safety and so forth? And then ask yourself, among all the different alternatives that are out there, especially now with LED lighting becoming more reliable and less expensive, is there a more efficient alternative? And in terms of pumps and motors, there almost always is. And with lighting also. Okay, let's talk about pumps and motors. Those are probably going to be the biggest energy users and energy wasters in any water or wastewater facility. Motors are pretty good at what they do, but they aren't perfect. Again, we're talking about the laws of physics. In most induction motors, energy is converted to motion by the proximity of a magnetic field, but not all of that energy is converted. Some of it is going to be lost to heat, to friction, and to resistance. Again, the laws of physics. There's not much we can do about these. Pumps are even worse at what they do. Not all of that rotational energy in the pump is being converted to fluid power. Again, you're going to lose some of that energy to friction, wear, and inefficiency. Inefficiency of the pump as designed. Maybe it wasn't the pump for the right pump for the job. Internal wear. A pump only delivers its rated efficiency the day it's brand new and first turned on, and it starts wearing out internally from that point forward. Okay, this is a term that you would probably see on any distribution exam anywhere in the country. This is wire-to-water efficiency. Motor output power, which is the power that is developed on the shaft end of a motor, will always be less than motor input power, which is the power that you are purchasing from your energy provider and paying for. That's the first law of physics. That's the first inefficiency, is the inefficiency within the motor. Fluid power, which is the energy that is developed on the discharge side of the pump, will always be less than motor output power, which we already explained what that is. The ratio between input power and liquid power is called wire-to-water efficiency. Again, you probably will have a wire-to-water efficiency problem on your distribution, or maybe even a treatment exam, wherever you are in the country. Let's take a typical problem and kind of illustrate it. let's say we have a 20 horsepower motor here and it's fully loaded, which means it's drawing roughly a little bit less than 15 kilowatts. Remember that one constant that's on a lot of our exams, 1 horsepower equals 746 watts. So we take that 14.9 kilowatts, multiply that times the efficiency of the motor in a decimal equivalent. In this case, we have a motor that's pretty efficient, let's say 92%. Take that result, multiply it times the pump efficiency. Now, most pumps that we see out in the field are not delivering 75% efficiency, but we will use that in this example. So what we actually get on the discharge side of the pump in terms of useful work is only 10.3 kilowatts versus the 14.9 kilowatts that we paid for. So the overall wire to water efficiency in this example is 69%. And what that means in dollars and cents, for every dollar you spend on energy, you get 69 cents worth of useful work. And that, incidentally, is one of the lowest margins of efficiency of any industrial use of electricity in the world, actually. And again, it's just because of the laws of physics. So when we look at our pumps, when you go and look at your pumps, you're going to be trying to find out some information. First, you want to get a hold of the manufacturer's performance curve for that pump, which most of the time should have been provided to you when the pump was purchased. You want to also have an idea of the motor specifications, and most of the time you can get that right off the motor nameplate that's attached to the motor. If the motor and pump are connected by some sort of drive or coupling, you want to find out what the information is on that. You'll already know what your design data is in terms of the gallons per minute that you need against the total dynamic head, and we'll talk about that term in a few more minutes. If you are qualified and trained to do what that person in the photo is doing and actually open up your motor control center with an amp probe, that's the instrument that that person has in their hands, and actually take running amp readings. That's one of the things that we do when we come out and do an energy audit. If you're not trained or you're not a certified electrician, I wouldn't recommend doing that because that can be very dangerous, but some of us are trained. And then you look at your existing flow conditions and whether those conditions are going to be adequate now. Will they be adequate in the future as your system changes, as your population goes up? When we go out to do an energy audit, we very often find pump efficiency less than 50%. And again, in terms of dollars and cents, that means less than 50 cents on the dollar in terms of work produced per dollar paid for energy. There was a study in Wisconsin quite a few years back now, at least probably 10 years. They went around and looked at over almost 1,700 different pumps, large and small, at 20 different process plants, water and wastewater and food production and packing houses. Many of the pumps that they found were operating way below 10% efficiency, and you don't want a pump that is operating at 10% efficiency. Again, that's 10 cents on the dollar for work done versus energy purchased. Very often they are that low efficiency because operators have throttled the valves for one reason or another. Maybe they needed to moderate flow, or in the case of a well pump, at certain times of the year, maybe the water levels were dropping in the well, and to avoid sucking air at the inlet, they actually throttled the pumps down by turning the discharge valve down. Very often pumps were oversized because facilities are often designed for peak capacity rather than efficiency. So the engineers are making design decisions based on the life of a treatment plant or the life of a project, which might be 40 or 50 years, and designing it to operate at the population that you might have in 40 or 50 years. So we have often seen pumps that are just pumps and motors that are way oversized for the amount of work that they're doing. And they are basically just wasting a lot of money on energy. And also the good old "we've always done it that way" mentality. And we're not about to change because everything's working fine. Okay, you should know a little bit about your system curve, and your water system or even your wastewater system has its own system curve. This is something that the operator can't change. The system curve is basically the relationship between friction head and static head. This chart, or the illustration on the left, is a good example of a system where as soon as the pump starts, it has to lift water high up a hillside. So the proportion of static head to friction head is much greater if you're lifting water a great distance vertically. The minute that pump starts, it is already fighting a lot of static head. This diagram on the right would be more like an irrigation system where you're not necessarily lifting the water very high up on a hillside. You might be pumping the water many miles through irrigation pipes over relatively flat land. So the system curve on a system like that would be a very steep curve. So as gallons per minute go up, the proportion of friction head to static head is actually much greater in a system like that does not have to lift water very high, but it may have to push water long distances at low elevations. So your system, probably you have a curve that falls somewhere in between these, and these obviously are not to scale, but I wanted to get you familiar with that term. The pump performance curve is provided to you by the pump manufacturer. It's the relationship between head and flow. Head being total dynamic head on this axis. All pump curves are pretty much the same, manufacturer's curve, as a function of gallons per minute or liters per minute on this axis down here. As the pump ramps up and flow increases, system resistance increases, resistance being dynamic head, and pump performance decreases. So basically, the more water we are trying to push through the pump, the performance of the pump decreases proportionally. Your operating point is how much flow you need at a given total dynamic head. Now, you know how much that flow is, or your engineer does, because he or she designed it to work within the parameters that you needed, your design data. Let's say you are pushing 500 gallons a minute to a tank up on a hillside that's 300 feet. So that is your duty point, how much flow you need at a certain head. The operating point is the intersection of your system curve, which is down here, and the manufacturer's performance curve, remember, which sloped downward. This operating point, that's where you want to be on the manufacturer's curve at the manufacturer's best efficiency point. And again, we do a full 6-hour in-person workshop on optimizing pump curves. And this is kind of the 30,000 foot elevation. And I just wanted to mainly get you familiar with some of these terms. When you start getting out your manufacturer's curve and you start looking at your own hydraulic modeling, and you actually get into the nuts and bolts of doing an energy audit. Let's talk a little bit about motors. I know I'm moving pretty fast, but I still have a lot of information to cover, and we do want to allow at least 5 or 10 minutes at the top of the hour, before the top of the hour, for questions and answers. Manufacturers, seems like about every year, manufacturers are squeezing a little bit more efficiency out of electric motors. That's important. Motor efficiency really does matter, just because of the sheer amount of energy that motors in the United States are consuming at any given time. 63% of all industrial electricity consumption is actually used by motors to move things or push things around. That includes water and wastewater. Almost a quarter of all the electricity produced in the United States is used to run just motors, and the manufacturers are aware of that. They're also aware that some customers are paying utility bills, in millions of dollars, and so they are trying to squeeze a little bit more efficiency out of motors with each passing year. And by and large, they're getting better and better at it. Average motor efficiency about 30 years ago was maybe 85 to 90%. Average motor efficiency, especially in the higher horsepowers nowadays, is in the 94 to 95% efficient. And again, that means 95 cents worth of useful work per dollar of spent on energy. There are 7 factors that influence the efficiency of electric motors. The first one is age. We just talked about that. Generally, the older the motor is, the less efficient it is. The capacity of the motor. If you have a 5 horsepower motor, it's very typical you might have 75 or 80% efficiency, nameplate efficiency that the manufacturer gave you. If you buy a 1,000 horsepower motor, typically you're going to see 93, 94, maybe 95.5%, especially if you buy what's called a NEMA premium efficiency motor. I'll talk about that in a few minutes. The third factor is speed. Generally, you can buy most motors in the United States in several RPM ranges. 3,450 is real common. The next step down would be 1,740. The next step down from that would be roughly 850 to 900. And the next step down from that would be 600. For a motor that is rated, that is loaded with the same work in terms of horsepower, the higher speed motor tends to be slightly more efficient. And that one surprised me. I would have thought otherwise. The type of the motor. Most motors in the water business, most motors used in US industry are what are called induction motors. The very largest motors that are moving water 24 hours a day, 7 days a week over mountain ranges and pushing water many hundreds or thousands of miles, they are called synchronous motors. And they have a much lower power to weight ratio. They tend to be very heavy, overbuilt. They tend to be very expensive. But again, they are slightly more efficient than induction motors. Maybe some of you might have some synchronous motors in your system, especially if you have some very high horsepower motors. The fifth factor is temperature. Temperature is a motor's greatest enemy. The whole idea is to keep the inside of a motor cool. As temperature increases, electrical resistance increases, and efficiency goes down. If you have your motor rewound, which many systems do, it can be very economical to go and have a motor rebuilt. And basically by rewinding, we mean taking it to a motor shop, having the end bells pulled off, all the bearings taken out, and an attempt made to stuff all the copper windings back into that motor that came out of it. That's what we call rewinding. And it generally gives you an almost brand new motor, but you will lose some of the efficiency that the factory put into that motor if you have your motors rewound. And there it is. My screen froze up there for a minute. The seventh factor is loading. In fact, all induction motors like to be loaded with about 75% of their rated horsepower. If you have a 100 horsepower motor, you want to have it doing about 75 horsepower worth of useful work. That's when you will get the highest efficiency in terms of work produced per dollar paid for energy. Again, sometimes when we do an energy audit, we see motors that are out there that are way underloaded because they were designed for conditions 20 or 30 years from now. Any motor that is loaded with less than half of its operating capacity in terms of horsepower is throwing a lot of money down the drain in terms of energy use. And you may have a motor like that in your system. So let's go through some real simple calculations when we're looking at motors. The kilowatts needed to drive a motor is a function of, and this is the equation, it's a simple equation, horsepower times 0.746 kilowatts times motor loading, and this is a decimal equivalent, divided by percent efficiency, and that's also a decimal equivalent, and I'll show you how that looks. The other factor is operating hours, which is just kilowatt hours times kilowatts times hours, and the simple payback. Remember, this is what we're trying to arrive at. When will this new piece of equipment be paid back in energy savings? And that's the cost, the upfront cost of the equipment divided by the annual savings in energy. So here's a typical question. And again, a lot of numbers here, don't try to memorize them all, but I wanted to get you familiar with the concept. Let's say you have a 10 horsepower motor. It's 86.5% efficient, and you'll get that information off the nameplate. And this motor is running 4,000 hours a year, and it's loaded at 70% of its rated horsepower. And your cost of electricity is 10 cents a kilowatt hour. And I'll tell you, a lot of people in California would be happy to get 10 cents a kilowatt hour. In many cases, it's 2 and 3 times that. So the question is, what's the cost per year to operate? That's the first thing we want to know, how much this is costing us every year to run this one motor. So we just run the numbers. Horsepower times loading times efficiency divided by efficiency is just a little more than 6 kilowatts. 6 kilowatts times hours that's how many kilowatt hours per year. Kilowatt hours per year times cost of energy is $2,416. Pretty easy, right? Just basic math. Now let's throw a little variable in here. What if we replaced this motor with one that was 91.7% efficient, which is more typical of what you'd see nowadays? Same operating conditions, same power cost. What would be the new cost to operate? So we just run those numbers again, but instead we use 0.917, which is the decimal equivalent for 91.7% efficient. We find now that that motor is only drawing a little bit less than 5.7 kilowatts. We run it out to the hours, we run it out to the years, and then we multiply that times our cost of power. Our new power cost to run that motor is a little bit less than $2,300 a year. So we have immediately seen some savings from jumping up to 91.7% efficient. So the bottom line is, what do we want? What is that payback going to be? How many years is it going to take to pay us back for that motor in energy savings? So let's say that motor had an installed cost of $380, which is pretty typical for a 10 horsepower motor. What would be the payback? Again, run the numbers. The original cost to operate, the new cost to operate with the premium efficiency motor. So we're saving $140 a year. Remember that that motor costs us $380 divided by 140. That gives us a simple payback of less than 3 years. Now, the typical operating life of a motor is 10 years or more. So in this example, the cost of this motor is going to be completely paid back in less than 3 years. And the energy savings beyond that just keeps compounding year after year after year. And again, if you have 20 or 30 motors like this in your facility, upgrading to premium efficiency can save you really a lot of money. That's, again, the bottom line of this workshop. Rewinding is, it's very tempting to go and have your motors rewound because it's less expensive than buying a new motor, and you are basically getting almost a new motor. But these are my rules of thumb. If your old motor is more than 20 years old and less than 40 horsepower, just go buy a new motor. I can almost guarantee you that energy savings will pay back the cost of that motor well within its lifespan. If rebuilding your old motor costs more than 30 to 40% of a new motor, just go buy a new motor. Again, and make sure the nameplate says NEMA Premium Efficiency. NEMA is National Electrical Manufacturers Association. I guarantee you, you will save money. Let's talk a little bit about lighting. This is really easy. This is what we call the low-hanging fruit because it's very easy for anyone to change out a light fixture. Benefits include lower cooling costs, lower maintenance, increased safety if you can increase the amount of light. And again, the bottom line is cost savings. Many of you have seen this little comparison. It's kind of obsolete because this is using an incandescent lamp, which are largely obsolete. Comparing it to the cost to operate for a CFL, and then the cost to operate the same CFL with an occupancy sensor because the room is only occupied 4 hours a day. So we go from $10.92 to $1.33. If we factor in LEDs, it drops about another 40%. So let's work the numbers on your lighting. You have 25, 27 watt CFLs. They're turned on 3,000 hours per year, and you're paying 14 cents a kilowatt hour. What's the annual cost? So we run the numbers, 25 lamps times 27 watts. That's 0.675 kilowatts times the hours per year. So now we have kilowatt hours per year, and now we just need the cost of energy, 14 cents a kilowatt hour. That gives us a cost to operate those lamps, $283.50. So let's upgrade. Let's go to LED now. So we get rid of those 27 watt CFLs. We replace them with the equivalent in LED would only draw 18 watts. And we still assume the same operating hours per year and the same cost. What's the potential savings by replacement? Again, let's just run the numbers, run the calculation. Take the same number of lamps, same hours, 18 watts. It goes down to you're actually saving $94.50 on energy. So now we need, again, the simple payback. Let's say the cost per LED is $2.50, which is pretty typical because costs are coming down. They're half what they were a few years ago. So again, we'll run the numbers. Simple payback is cost divided by annual savings. The cost in this case, the upfront cost is $165. So we take that upfront cost divided by the energy savings, and the cost of the retrofit, again, is paid back in less than 2 years. And the lifespan of an LED is many thousands of hours. So again, this retrofit to LEDs will be fully paid back in energy savings. And again, savings beyond that point are just keep compounding year after year. So let's talk a little bit about HVAC. I want to wind up ahead of the top of the hour so that we can get time for some Q&A. You'll see that acronym HVAC, that's heating, ventilating, and air conditioning. It's designed to provide comfort, humidity control for equipment, humidity control for ourselves. In commercial buildings, it's a large percentage of energy use, but in water and wastewater treatment plants, really much less. Pumps and motors are really what's gobbling up the energy in our water and wastewater plants. Some terms that you might want to know when you're shopping for HVAC equipment. We have what is called seasonal energy efficiency ratings, or seasonal energy efficiency ratio, and the SEER. Now, these are U.S. Department of Energy ratings, and there's a big yellow sticker on when you go shopping for these, and you'll see these SEER ratings. For in terms of home units, which are 5 ton and under, it's SEER. It's EER for over 5 ton. And a ton of cooling capacity is defined as 12,000 BTUs per hour, in case you've heard that term. This is what we mean by the older the equipment, the less efficient it is. If you have an old air conditioner or an old furnace from before 1970, typical SEER was 6. Nowadays, actually, it's higher than this, but from 2006 to 2010, the industry-wide SEER is now up to 13. And again, that's BTU per hour of cooling power divided by watts consumed. So there's a lot of efficiency that's being engineered into new HVAC equipment. These are the 2019 minimums, again, based minimum Department of Energy ratings. You can see it varies depending on what part of the country you're in. So if you're in Arizona or New Mexico or California, it's 14 minimum, no matter what the size of the unit. Again, the southern part of the United States, the requirements and the standards are higher than the northern tier of states. Again, just because in the summertime, it doesn't get nearly as hot, the northern tier of states. Heating is basically, and my screen keeps freezing up here. Heating can come from all kinds of different sources. You can see them listed there. We have gas, fuel oil, wood, thermal transfer, which is allowing the sun to heat up, say, a big cinder block wall or a concrete floor through open windows during the day. And then during the night, all of that stored heat that was radiated into the mass is allowed to radiate back into the room. Electric heat is always 100% efficient. Natural gas is roughly 80% efficient. And again, that's industry-wide. Consider all of your different fuel costs when you're comparing heating. These are some of the fuels that are available. Again, heating is measured as British thermal units, and you might see these terms on your gas bill or your energy bill. 1 therm is equal to 100,000 BTUs. 1 kilowatt hour is equal to a little bit more than 3,400 BTUs. 1 gallon of fuel oil will provide 139,000 BTUs, and a pound of wood is about 9,000 pounds. So just some terms and how they compare, and terms that you might see on an energy bill. So in terms of energy conservation opportunities for your HVAC, regular service and inspection is always a good idea. Make sure you're changing your filters regularly, and I really recommend, most of you probably have programmable thermostats in your homes. It's a surefire way to save money on energy. A 10-degree reduction over 10 hours will save 10% in total energy cost to run an HVAC unit. So, and the cost for a programmable thermostat is usually less than $50, depending on how sophisticated they are. Here's some resources real briefly. These are some really great guidebooks that are available. These are PDFs that are available for download. This one is at the top, that is. The U.S. Department of Energy runs a department called the EERE, Office of Energy Efficiency and Renewable Energy. There's an organization called focusonenergy.com. They have a very nice water and wastewater best energy practices guidebook. It's a little bit old, but it's still very relevant. And that pretty much is the end of my presentation, and I wanted to turn the floor back over to Savannah to see if we can address any questions that came in.
Of course. So we did receive a few questions, so I'm just gonna start from the top. So an attendee asked, do you determine motor loading by measuring the amperage draw and compare it to the nameplate amperage of the motor?
That is exactly how, that's one of the ways that we determine motor loading. Another one of the ways when we cannot, for safety reasons or for other reasons, we can't get into the panel to measure running amperage, is we'll turn the motor off and we'll put a reflective piece of tape on the shaft if we can get to it, turn the motor back on, and we use a laser tachometer to measure the actual shaft RPM of the motor. And if the motor, say, is rated at 3,450 RPM, but it's actually driving, say, 31 or 3,200 RPM, we calculate motor loading that way. That's a great question.
Wonderful. An attendee did ask if you could switch back to one slide prior to this question and discussion slide so they can look at the resources. And I know we'll be posting these slides by the end of this week, but thank you for that.
And is that the slide right there?
That's the one.
Okay, yeah, I'll leave that on the screen and we'll take some more questions.
So the next question we received is, how do adjustable frequency drives affect the efficiency of pump motors? Does this negate some of the waste of oversizing motors?
This does. Variable frequency drives or variable speed drives, they're kind of synonymous. In water pumping applications, they almost always provide energy savings, and they do that for various reasons. Number one, they can ramp a motor speed up or down depending on conditions in the system. Rather than having a motor cycling on and off to meet demand in the system, a variable frequency drive is like the throttle on a car. You don't drive your car with your gas pedal floored and then pumping the brakes to regulate your speed. You want to just slow the car down. That's what a VFD does, variable frequency drive. It also has what's called inherent power factor correction, which power factor is the ratio of active power to reactive power. Reactive power in a motor is power that we pay for but produces no useful work. And mainly that power is just used to set up magnetic fields. And the variable frequency drive actually has inherent power factor correction, which basically means that all of the energy used to run the motor is active power and not reactive. And there is a little slight amount of energy loss converting your incoming voltage to DC and then running it through a rectifier and then regulating it out as AC again. But in most water pumping applications, you almost always see a reduction in energy cost.
Thank you, Neil. So I guess we're receiving some questions right now as well, but to piggyback off of that question, an attendee did ask how much energy is saved by using VFD motor drives?
That the amount of energy saved depends on how variable the loading is. And that's sort of impossible to answer because it would depend on the demand in your system. For example, if you had a motor that at 6 p.m. when everyone is using water is running at 100% speed, and then that motor could just be throttled down to about 10 or 15% of its rated RPM at 2 in the morning when hardly anyone's using water, you would have a much greater amount of energy use reduction. I can send that's a great question, and I can send some examples by email if anyone would want to see those examples.
Yeah, let's you and I talk offline, and we can provide some of these examples in the follow-up email that goes out to all of the attendees. So we can definitely get that going.
Yeah, it's hard to answer a specific question like that without knowing the actual percentage of ramp down and for each hour of each day, and then we could calculate it. But yeah, we can send some resources.
Perfect. So we're getting a ton of questions. So I'm gonna pick 2 more, and then for the folks that did submit some questions, if we're not able to answer them right now, we will follow up with you offline. So the next question we have is, what are the biggest obstacles that prevent small and frontier city operators from proactively conducting audits and upgrades regularly?
For small communities, the biggest obstacle we've seen is your budget. This is why a lot of folks actually have motors rebuilt and rewound each time they burn out, because they just don't have the money in their operating budgets to go out and buy new equipment, and also the political will to do it. Very often it's a matter of trying to convince your decision makers to make a very large upfront capital investment and describe to them how it will save them money in the long run. It's getting people to look at life cycle cost rather than initial cost. And that's often a very tough sell, especially when a community is disadvantaged and is short on money. And also, the desire to actually do it, and then also the awareness of how much money can be saved. And that was one of our goals for this seminar.
Thank you, Neil. So the next question too, an attendee asked if you would comment on pump efficiencies when considering the wise selection of motor voltage and motor speed or number of motor poles.
That's going to depend on your duty point. In other words, how much flow you need at a given total dynamic head. That's almost an engineering question, and That's one that we can probably save for an email response because that's pretty technical. And I know we're down to the last few minutes. So let's answer that one by email and I'll send some information.
Perfect. You want me to rattle off one more question for you?
Yes, absolutely.
All right. So an attendee asked, where would you recommend finding a company to help with an energy audit?
The Association of Energy Engineers, AEE, they have a website, aee.org. The American Society of Civil Engineers, ASCE. If your own civil engineer, if your system has a city engineer or you have a design engineer that works for your system, they are plugged into sources of energy auditors. Also talk to your environmental finance centers. Also talk to your RCAP partners, depending on where you are in the country. If you're in the West, you can talk to us, rcac.org. You can go to that slide I showed at the beginning. All of the RCAP, the 6 RCAP regions have resources for energy audits, especially the Great Lakes RCAP. They're very active in doing energy audits, and they have government grants to do those.
Great. That sounds wonderful. So we will definitely follow up with folks and get some of those specific questions answered by email. And so I guess to wrap up, thank you, Neil, for being here with us this afternoon to provide your expertise. That was a phenomenal presentation. And I do just have one last poll question for folks that are still on the line. We do offer technical assistance through the Environmental Finance Center network. So if you would like to learn more about how we can help you with some of your topics outside of energy efficiencies as well, and get you connected to some of the experts that we bring onto webinars and throughout the country, please let us know now. And I'll leave this open for just a few more seconds, and we'll get ready to close this in 3, 2, 1. And then lastly, in the chat box, there is an evaluation form that's going to be sent out. If you could just, give us a few comments about how you thought today's session went, that would be wonderful. We definitely utilize this feedback for our future webinars. So again, thank you, Neil, for being here. I'm going to pass it over to you for any comments.
I would like to thank you for the great job you did in moderating and for fielding all those questions. I know we'll have a lot of great information to send out to people after this is over. I'd also like to thank the Environmental Finance Center for also, you're in Region 2, is that correct, in Syracuse?
Yes.
Well, I would like to thank EFCN, the whole Environmental Finance Center network, for allowing us to do the workshop, and it's been a pleasure.
Thank you so much, Neil. All right, everybody have a great afternoon, and we'll be in touch with the follow-up materials. Thank you.